Welcome everyone to the workshop on Introduction to Drift Detection by Ashley, Scillitoe, and Shee from Seldon. So with a background in cloud computing and passion for machine learning, it has combined those skills and now works in the MLOps field, where he heads up developer relations at Seldon, organizer of Tech Ethics London and MLOps London. It is heavily involved in lots of developer communities and thankfully loves both beer and pizza. And Ashley is a data science research engineer at Seldon, where he works on developing production-ready tools for drift, adversarial, and outlier detection. Prior to joining Seldon, he spent a number of years as a research fellow at the Alan Turing Institute. Here, he explored the use of machine learning for tackling aerospace engineering problems with a focus on explainability and uncertainty quantification. Ashley also completed a PhD at the University of Cambridge and is a keen proponent of open source software. So with that introduction, I hand over the floor to our speakers, Ashley and Ed, and thank you.
Great. Yeah, thanks so much, Ashley. We'll just get the sharing up and then we'll dive into the slides and the workshop that people can run through. Just something to mention, as you know, just as we get started here, this is much more fun for us if it's super interactive. I know it's hard to do when we're virtual and everyone's online, but stick questions in the chat. I don't know if you're able to unmute at all, but if you are, unmute and ask questions as we go along. But if not, throw them in the chat because we've got it up on another monitor next to us, so we can keep an eye on that and answer things as we go along. Particularly as we get into the workshop element and people are running through things themselves, there may be places you get stuck or you just want to ask more. So yeah, with that, you've had a great introduction from Ashley. I'm Ed. This is Ashley. We're based out of London in the UK. So you may have noticed it's kind of getting pretty dark over here. Unfortunately, we couldn't make it to Toronto this year, but we'll see you all next year for sure in person. And today we're going to talk about drift detection. So this is aimed as a beginner guide. You know, it will obviously help if you have a bit of an understanding of machine learning and the concepts underneath and some of the frameworks. But it's from, aside from that, right? You don't really need to know what drift is. We're going to go through that. So we've got a very quick overview of what we'll do. So we'll go through what is drift. We'll talk about why you should detect drift, and then how to detect drift as well, right? And because I think those are the three really important questions you need to get out of the way. And then we'll jump into a workshop, and you guys can work through it yourselves. As I said, ask for help if you need it, yeah, we'll go from there. So to kick off, right? Let's look at first why we do machine learning, right? So we're at the base level. What we're trying to do is predict something in a real world task, right? And we train this model, let's call it M, to estimate what the outputs might be. Now, what we're going to use just for the sake of visualizing some of the different types of drift, we're just going to use a very simple binary classifier here. So we've got orange blobs, we've got blue blobs, right? And then we have some sort of decision boundary, and you can see on there, there's a true decision boundary line where that black dotted line is. Now, that obviously most of the machine learning use cases we have are far more sophisticated, and you'll see as we go through this how there are different algorithms for different types of machine learning model and different modalities of data and so on. But for understanding the main principles, let's work with this really simple example. And so that's what we're trying to do with a machine learning task, is some sort of prediction or classification based on some sort of real world data set that we've had or collected. Now, what we find is that performance on held out data, a test set, for example, gives us some sort of estimate of future performance. Hopefully, as Ashley points out, right? But what we're making there is a huge assumption, we're making an assumption that the process underlying X and Y, so the inputs and outputs of our system, remain constant. And what we'll find is that in the real world, right, things actually are subject to change, believe it or not. And there are a lot of different ways in which the system's inputs, outputs, and relationships can change. So we've kind of talked about the motivation. We've said we're using the past, trying to predict the future, and in reality, that's not actually the case, right? But the important thing is let's try and identify when this happens. So what is drift? So drift is when the process underlying the inputs and outputs of your system in deployment differs from the process that generated in the training data. So essentially, we're saying we've got some sort of reference set over here, which is normally the training data, or a test set or something like that. And what we're seeing in the real world differs, right? And we're trying to detect that. And some of the kind of knock-on effects of this, so that you maybe can no longer expect the model's performance during deployment to match the that was observed on held up training data. So if we held up some data for a test set, we got a certain model accuracy, we might not expect the exact same accuracy in production. And then what we'll do is we'll talk through the different types. So the first of these is covariate drift. And what we're saying here is basically the inputs to the system, the distribution of those has changed significantly such that there's been a significant change in that, but without affecting the underlying relationships of the system. And I'll give you an example because it's probably the easiest way to explain this. But it's a change in the distribution of the input data, often referred to as input drift as well. And if we use our visualization with our kind of classification example with the orange and blue blobs here, we can see that maybe covariate drift would be an example where actually in the real world, which we're seeing on the right-hand side, we're getting production data that the classification still looks good, but we can see that the values of the orange blobs have shifted significantly in terms of the inputs of features that we're feeding into our system.
So we've got a question there.
Oh, a question already. Right. Yeah, perfect. Let's go straight into it. So does drift can also be referred to as Does drift can also be referred as overfitting, which is performing well on training set, and how do you relate data drift with overfitting? Do you want to?
Yeah, I can take that one. Yeah, good question. No, they're slightly distinct things, really. So and that leads on to something that we will cover later regarding overfitting, but generally. So overfitting, underfitting, that is those are terms to talk about how the model is performing during training. And when we say overfitting, we're saying, you're overfitting some training data, so it won't generalize to essentially held out training data, validation data. So you get overfitting even if the validation data is drawn from the same distribution as the training data. They're not, whereas drift, we're actually saying the test data, the deployment data in this case, is not just different instances of data, but the distribution representing this data has actually drifted, so it's different from the training data. So they're slightly distinct things, but they can be related in a sense. If you have a heavily overfitted model, it probably it generalizes less well, so it could be more susceptible to drift.
Mm-hmm. Yeah, so and the other thing to point out is that what we're looking at with drift often is the distributions over time, right? Whereas overfitting might be like a static thing you look at and you say, we trained it and then we evaluated it and found that it was overfitting. With drift, you might evaluate it, find it's totally fine, put it into production, find it performs exactly as you expect. But then, 3 months down the line, things are starting to change. And so that's the fundamental difference that we're looking at. A couple of other points that have come in there.
Yeah, I think I'll take Enrico's one. I think Enrico's probably asking, in this particular example we're showing, the model, he's asking, would the model still be just as effective in terms of like whatever performance metric you're looking at? I guess like classification accuracy here. And yeah, you're right. I mean, you could say that's a good or bad thing. Yes, in this particular case, the Y1, the orange data has drifted, but actually it's still the right side of the decision boundary. So yeah, the model will still perform well. You could say that's a problem because something pernicious and horrible could have happened to your data here, but if you're just monitoring model accuracy, you're not going to notice because the model is still giving you good accuracy here. So yeah, it's an important point that drift can be harmful in terms of model performance. It cannot be harmful. That's not always linked to whether you care about the drift or not.
So that actually ties super well into the example I was going to give for covariate drift. So yeah, just quick reminder, covariate drift is the change in the distribution of inputs, but not necessarily affecting the actual underlying relationships of the model. So here's an example, right? Let's say we build a facial recognition classifier and we train it and evaluate it and deploy it, and we're seeing images like this, right? And it is performing exactly as we expect. And then something like this happens, right? Now, who here wants to guess the difference between these images, right? The answer is, to the human eye, there's very little difference whatsoever. But what you'll actually find is that like the image on the right is slightly desaturated, it's slightly darker than the one on the left. And whilst to the human eye, we might not detect a change there, our classifier is receiving slightly different inputs for those pixels of the image. Now, why would this happen in the real world? It could be something as simple as like your camera that you've set up to do the facial recognition is slowly gathering dust. Your images are over time going to become more and more desaturated, they're darker and darker. And eventually, this might drastically affect how well your system performs. So this gives you a really good example of how something very subtle that we might not notice is important to start monitoring for, because over time, it might have a drastic effect on the way things behave. I'm going to jump through the types of drift first, and then we'll go back to some of the other questions people are throwing into the chat. But great that you're all engaging. This is much more fun for us like this, so thank you. Okay, so second type of drift is prior drift. And here, we're basically looking at like the other end of the machine learning system. So what we're saying here is that there's been a change in the distribution of outputs of the system, whilst the relationships between the inputs and outputs still hold true. And this is often referred to as output drift or label drift as well. Again, probably the most academically mentioned name is prior drift, but yeah, you see it referenced as everything. And again, if we look at our blue and orange blobs that we had as our reference distribution on the left, and then our drifted data on the right, you'll see, and Enrico pointed out earlier, that like your classifier still might be performing perfectly well, but what we're seeing is like a drastic increase in the number of classifications that are coming out blue. Now, those might be correct, and there's nothing wrong with that, but I'll give you an example here of why, again, you'd want to monitor for that. So let's say we're a bank and we're doing some sort of automated loan approval based on all sorts of features. It could be how much money you have in your account, what's your credit score, did you pay your credit cards on time every month, all sorts of things. Now, we might not see a drastic change in the input distributions or in the underlying like concept of the model, but we'll find that like over, let's say, a month window, we're approving far more loans than we normally do, right? That's something we want to know about, because as a bank, we might not even have enough money to hand out all those loans, but we also might be massively overexposing ourselves. Let's say we put aside like 10% of our revenue to hand out as loans. Suddenly that becomes 50%. We're at risk if people start defaulting on them, particularly at times like now where people were able to take out loans over the last couple of years at really low interest rates. And now, with a kind of global recession looming, interest rates are raising everywhere. Suddenly people might start defaulting on those. We've put our company at risk. So we need to be able to identify when the distributions of the outputs are changing. And then the final type of drift that we'll encounter is concept drift. And this is where the actual underlying relationships of your machine learning model have changed over time. So again, if we look at our reference distribution on the left, the blue and orange blobs, we'll see that actually now the truth classification line has changed. And this is a good indicator that we probably need to retrain or build a new model. And again, give you a nice example here so that you can kind of understand it. I imagine nearly all of you, as you've delved into the world of machine learning, have at some point built a house price prediction model. It's like the hello world of machine learning. We know how we can use all sorts of features, number of rooms, where it is, square footage, whether it has a garden or not, etc. And we can build very accurate models if we have enough classification points. Now, let's say you built and trained that model at the beginning of 2020, and you evaluated it, and it looked fantastic, right? And over the first couple of months of 2020, it's doing super well. It's almost exactly telling what a house will get sold for. But then the pandemic hits, right? And buying behaviors change massively because everyone wants to work from home or has to work from home. And so they want a spare bedroom. So now larger places are more desirable. And places in the city center that used to command like a huge price now become a lot cheaper because nobody's commuting in. They don't need to be jammed into the city center. They want to be out in the countryside where they've got outdoor space and they can exercise and see people in their garden, right, whether it's allowed. And that human behavior has driven a drastic change in the way that the underlying relationships between the input and output of that model work, right? So that particular example, obviously, we need to go and investigate further and then maybe look at training a new model just on, post-COVID data. Cool. Okay, so then the next section is why detect it? And hopefully you've kind of picked up on some of this already from the examples we gave. But as we look into this, do you want to pick up from here and talk about why detect drift?
Yeah, sure. So why detect drift? Well, so to give us sort of an example here, we just we've drawn a nice simple sort of ML deployment. So we have some training data, input data, output data. Again, this is just a binary classification example. We use that training data to train a model, and then we deploy that model on test or production data. Okay, and so the first big point is that knowing whether this model can be trusted is more often than not business critical for all the sorts of reasons that Ed has just talked about. So that's fine. And if we have labels, we can monitor the machine learning model's performance. We have that ground truth. We can measure whatever you're interested in, F1 score, MSE, this regressor. And we can look at that model performance metric to understand if the model is performing well. But often in deployment, labels are not available. And final kind of important point, the drift is often not observable to the human eye. So if you think about that, the example with the faces or the face that Ed showed, I could not tell by looking at it that those two images are drifted. These are all reasons why we kind of need some of the methods that we're going to talk about today. We need more advanced methods to monitor and detect drift.
I'm just going to jump in and show you a couple of questions quickly. So going back a little bit, question about the third types of drift. Concept. Actually, Enrico's replied. Thank you, Enrico. So the third one where the underlying relationships change is called concept drift. The first one we talked about, which is the change in the inputs, is covariate drift. Then we have the output drift or label drift, which is prior drift. And then the actual change in underlying relationships, or the concept, right? Easy to remember, concept drift. And then, sorry, I jumped it.
Yeah, that's
back again.
And I think just to cover the question that Mariam asked, the first question. So this is, basically just the response to that is that just to make the point that these different types of drift we're talking about, they're not techniques or kind of things to use. They're just things that happen and things that we need to monitor. Okay, so do you want to talk about this?
Yeah, I'll touch on this one actually. So this, in terms of why detect drift, we talked about that example of concept drift of house price prediction, right? But you don't even need to use that hello world example and imagine it, right? This did actually happen in real life. So it's a company called Zillow. I'm sure some of you are familiar with it. They basically thought they could build such an accurate classifier that, or house price predictor, that they could then identify houses that were underpriced for a market and then try and buy them and flip them for a profit, right? So they use this machine learning model in their iBuyer algorithm. And the idea was, flip them for a profit, right? It'd be great. And they heavily leaned in on this. And as you can see on the right-hand side, and kind of Q3 2021, they started buying up loads of houses because they identified all these ones they thought they could make a load of profit on. But the machine learning model had over predicted valuations because it had all been based on historical data up until 2021, right? It didn't account for the changing market, which obviously they were unlucky that they bought up tons of houses at the end of kind of 2021, and then beginning of 2020 we had a global pandemic which drastically affected things. But the algorithm they had continued to buy up homes, and they hadn't identified that this drift was happening. And actually what happened, I don't know if I know on this, you can see the share price, right, obviously plummeted, but they lost, I think the value was $80,000 on average per property that they had bought. So they ended up like making a massive loss, right, when you look at the number of homes purchased. So yeah, that's that kind of a real world example of that house price one. I'll pass back to Ashley, who can talk about how we detect drift, right? Now that we understand what it is, why it's important, and why we should detect it, how do we actually do that?
Yeah, thanks, Ed. So Enrico just points out, wouldn't some combination of covariate and label drift be equivalent to having concept drift? Not quite, but actually, in some ways yes, in some ways no. So Enrico is totally correct, actually, that these very rarely happen in isolation. So we separate these types of drift into very nice sort of mathematically well-defined things. So, for example, we officially say covariate drift is when your marginal P of X is not equal to your reference, P of X ref, whilst your joint distribution P y given X is equal. But actually, normally they don't happen in isolation. So usually when you have one of these happening, the other will very often be happening as well. So yeah, good question. Normally they kind of all happen at the same time, or often. Okay, so now how to detect these different types of drift. So that's kind of a big thing that we want to look at and talk about in this workshop. So we're going back to the same graph that or Ed or we both showed earlier. Right, so I'm going to talk about this by sort of talking about a number of different building blocks, and we'll build up complexity and kind of cover them as individual things. So the first building block is actually what do we want to monitor. So we've got this simple kind of ML deployment. We've got our model being deployed on deployment data. And so the first thing we can monitor is we could monitor the machine learning model's performance metric directly. Now, of course, we can only do that if we have access to the ground truth or the labels. So that's a nice thing to do, because then we're monitoring actually the drift that is harmful to the model. But of course, we don't often have access to labels, so we can't always do that. Okay, so the next thing we could do is we could monitor, if we don't have labels, we could monitor the model's uncertainty or confidence. And this is a really cool thing to do. So we can basically say, if we have a model that has some notion of uncertainty, so if it's like a Gaussian process or a neural network with dropout layers, we could get some sort of approximation of how confident the model is in its predictions, and we can monitor that. So if the model suddenly becomes less confident, that's a sort of indicator that there might be drift. And the final thing we can do, and this is perhaps the most widely applicable, but for reasons that we'll discuss, and the main one being the dimensionality, we can monitor the input or output data, the X or Y of our system. So we can monitor these data streams directly for drift. So this is widely applicable because you always have input and output data. But often this input data is either just super high dimensional, or it could be images, text, graphs. It could be something that's not necessarily easy to feed into your detection algorithms directly. So it's the most widely applicable, but the most challenging. Okay, so there's all these different things we can monitor, but how do we do that? Well, at least what we do at Seldon is we distill this down into a task of comparing two distributions. So we have P of Z ref, and the reason I say Z here is because Z could be X or Y. It could be, or even it could be like a model loss stream. So Z doesn't have to be like input data X. It could also be Y, your outputs, or a model loss. So we've got P of Z ref, which means your reference data. So this is typically the data that you use to train your model and validate your model and so on. And then you have P of Z, the red line here. So that is, I think we're being kicked out.
No. These are motion sensitive lights, but they're very unsensitive.
And so we have P of Z, which is, Z is like your test or deployment data. So it's data that's coming to you in deployment, and we want to say, the exam question here is our distribution P of Z equal to our reference distribution P of Z ref? If they're not equal, that means your deployment data is drifting from your reference data, and that's something you'll want to action on. Okay, so how do we answer this question? Are these two distributions equal? Well, we compute a test statistic or distance or similarity measure. So essentially we have S of Z, and there's loads of different ones, but the main thing is we want S of Z to be large if drift is occurring. Otherwise, we want it to be small. Right, so what can these test statistics look like? Well, we have loads of options here, but essentially we can mainly categorize them as either we can do univariate tests, univariate two-sample tests. Example of this is a KS test. So KS, just as an example, it's the test statistic is just the maximum distance between these two density functions. And if they're univariate, that means you basically do one test on each feature. So each feature has its own distribution, and you do a separate test on each feature. The nice thing about these guys is they're super lightweight and simple. You can get most of these tests on SciPy, the Python package. But the big problem with univariate tests is that they can lead to miscalibration if your features are correlated. If you're talking about something like images, you're very likely to have correlation. The other sort of big class of tests is multivariate tests. Big kind of one we use a lot is maximum mean discrepancy. So for these, you're doing your tests on all your features, all your dimensions at once. These are much more powerful, but much more computationally expensive. They often have really horrible quadratic or cubic scaling, so they can get quite expensive to do. But we get around that by we spend a lot of time coding out really high performance implementations on GPUs. So you can run these super, I wouldn't say efficiently, but super quickly, as long as you have a GPU, which lots of people do these days. Is that a good time to stop, or should I keep going?
I think no, keep going. I'm going to answer. There are a couple of questions in the chat. I'm just going to type to them, and so you can keep going with the
Perfect.
explanations.
Okay, so yeah, that's great. So yeah, just a summary. We want to find the distance between two distributions, and we do that by computing a test statistic. That's great. We have our test statistic. Now, the next thing is the hypothesis test. And why do we need that? Well, basically, we have a test statistic. I've just done like a little 2D example here. So what I'm showing here is I have a 2D reference distribution. And I've reference data that I've drawn from a distribution. I've just drawn it from like a standard zero mean unit variance normal distribution here. So it's just a nice circle. Got my reference distribution, and I've also drawn a test distribution, P of Z. And I've actually drawn both of these from the same distribution. So you can see the orange or red points are essentially lying on the green ones. However, now when I compute my MMD test statistic, or MMD squared in this case, you see it's close to zero, which it should be because I'm drawing both of these sets of points, these instances from the same distribution, the same normal distribution. However, this MMD squared is not precisely zero, it's 0.018. And why is that? Well, essentially, we don't have drift occurring here, it's just noise. It's just, this happens when you don't have a lot of observations. We've drawn a small number of observations from this distribution, and so the test statistic is not precisely zero. Whereas if we, as kind of a counterexample, here I've drawn my P of Z from a distribution which has drifted. It's like the x1 is offset, so you see all the points are kind of offset to the right. And so we expect, unsurprisingly, the MMD is more than zero here. It's 0.2. So we have a big test statistic telling us P of Z is not equal to P of Z ref, and that's because we have drift. But the question really is, how do we know at what value of the test statistic do we say it's drift, and we don't just say it's a little bit of observation noise? And that's really the kind of the difficulty or the challenge is, at what point do we categorize it as drift? Luckily, we can do that in a nice kind of statistically principled way. We do that by constructing a hypothesis test. So our null hypothesis, H of 0, is that P of Z is equal to P of Z ref. So essentially we're saying there's no drift. Our alternative hypothesis is that H1 is that P of Z is not equal to P of Z ref, i.e. there's drift. Once we've got a hypothesis, we can compute a p-value. And so the way we do this depends on what the statistical test is, but there's various ways to do it. But essentially what this p-value tells us is it's the probability of seeing such an extreme test statistic, in this case MMD squared, given that our null hypothesis H0 is true. In other words, to simplify things, if your p-value is small, it's highly likely that what you're seeing, this difference between the two distributions, is caused by drift and not just a little bit of observational noise. And so just to repeat, that's if your p-value is small. So what we do is we kind of come up with a threshold alpha, and we say if our p-value is less than this threshold, then there is drift. And typically this alpha will just be like 0.05 or 5%. And yeah, so that's it basically. That's kind of the rough building blocks in detecting drift. But then of course, you don't want to code all this stuff up yourself. So we have a nice open source library called Alibi Detect that we build here at Seldon. And this is a Python library, so you can just go and do a pip install. It has algorithms for what we're going to talk about today, drift detection, but also outlier detection, adversarial detection. And then, I mentioned before that some of these drift detection methods are computationally demanding. We code up this library using, it has TensorFlow, PyTorch, and also scikit-learn backends. So it kind of harnesses PyTorch, TensorFlow, and even a new library called KDOps now to make sure it's super efficient. It can run very quick on whatever GPU hardware you have. And to show off this Alibi Detect library, we're going to go through like a nice simple notebook, which I'll share the link in the chat in a second. This is basically on a use case which is classifying species of penguins, these cute guys you can see on the right. So I'll share the link and then I'll just check in with you, Ed, to see if there's any questions you think we should answer now.
Yeah, what we'll do is we'll open the workshop and then people can get started with that, and then we'll answer some questions live, because I think it's probably a bit more exciting. I'm going to type this one because it's easier to type. KOps, that's the one to marry in there. But there was, So everyone's got the link. You can jump into that Colab notebook and start working through. Again, stick questions in the chat. We'll go back to some of them. How far up are we going? I think you answered this. They're cut off to determine the difference between noise and drift. But you talked about p-values and the.
And just to elaborate on that, this cutoff is not. It's not just like an arbitrary number. The nice thing about this is it's essentially then your confidence threshold, and so you can choose a cutoff depending on if you care more about false positives or true positives. Any of you familiar with like ROC curves? It's just the same thing, that you can choose like a threshold to give you the sort of the chosen sensitivity and specificity that you desire.
Someone asked, what if some features are statistically drifted but some not? I guess it depends on the drift detection algorithm you're using. So some of them do like feature level importance, and others won't do. And so it depends like what it is you want to monitor for.
Yeah, for sure. And so that's a really good question. I probably should have mentioned that on this slide actually. That is one reason why you might choose to use univariate tests instead of multivariate. Because if you use univariate tests, you're doing a separate test on each feature. So you get a separate p-value on each feature. So you can actually look at a feature-wise level, what features are drifting and what features are not drifting. So you get that sort of like feature level attribution, which might be important for some applications. For something like image data, there's kind of no point doing that. It's probably not going to be very helpful to tell you that these pixels are drifting and these aren't. So yeah, really, it depends on like tabular data. You might care about knowing in particular which features are drifting.
And then if sample sizes are large, don't p-values start at 0? Does that start greater than 0? It's kind of, can't tell if that's an arrow or not, the way that it's been like cut into a new line.
I don't know if you mean p-values or. Yeah, so in the example on the left, maybe if you clarify, but if the example on the left, if the sample size was large, in the example on the left, when there is no drift, you would expect the test statistic to be hopefully closer to 0.
Yeah, so he's clarified it is an arrow. Yeah, p-values tending to 0.
No, so your p-values are essentially telling you this, that the likelihood of getting extreme MD squared, given that if your null hypothesis is true. So your p-values basically, they'll tend to 0 if there is drift, otherwise they'll kind of be above 0, closer to 1. So no, your p-values won't tend to 0.
Yeah, it's the sample size shouldn't impact it. Obviously, the larger your sample size, the less likely it is you get an unlucky, sample from the distribution, if you see what I mean, and therefore the less likely you detect drift. And that's why it's important to try and use large sample sizes if you can. Obviously, that's not always the case. If you're doing it on like a live drift detector, and you only get like a couple of requests a day, it's going to be really hard to monitor, to gather a large batch of data to be able to compare to some sort of reference set. But equally, there are other ones where you might have like thousands of requests per second, so it's really easy, and you can run online drift detectors that have much smaller sampling windows.
So should we answer one more and then move on to the...
Sure, yeah, there's some people messaging, which you pick one out. I think actually people are chatting amongst themselves. Sapphire says, what do you think actually on their, I guess on their conversation?
Maybe we'll follow up on that one, Sapphire, if that's okay. We can come back to that at the end, or and talk to you afterwards as well.
Tell you what, let's do this one from Harper quickly,
Yeah.
because people are voting it up. So what actions do we take once we've detected drift in a feature or multiple features?
Yeah, so well, that really does depend on your use case, your application. There's once you detected drift, it might be that you simply retrain the model. If you're happy that the drift is not indicating that there's a serious problem with your data, maybe it's just you increase the sort of cadence that you retrain your model. It could be that you take some sort of business action. If it's like the loan example, it might be you have to. It's not just about retraining the model; it's about like stopping loans or something. So yeah, it really depends on the use case.
Yeah, I like to say that the what you're really doing here is you're basically just using the drift detector to flag something for further action, right? Because and probably the first action will be some investigation by data scientists, but even looking at the data doesn't necessarily identify what a problem is. So, I don't know, even if we use the simple house price example, you might look into it and notice that there are certain distribution changes, but you can't really figure out why. And then you realize actually only once you've spoken to somebody who works in the property market, who's been following all the legislation and so on, they realize that your local government have brought in a rule that stops foreign people buying houses, right? And that's why you're seeing a dip on a certain particular, maybe it's like a particular type of property that's very popular to foreign buyers, for example. Now that's the kind of thing that, however much you look at the data, you're probably not going to draw that, or not going to draw the correct conclusion. So you have to combine it with business and industry knowledge as well. But the importance of drift is flagging this early so that we can do the further investigation.
Yeah, sure.
Cool. We do have more questions. I guess so. My question to you lot is that we plan to run through the notebook. We can do that, and also just take a lot like questions as we go, or we can just keep doing questions for now, and then if we have time, we'll run through it later. I guess it depends. Someone's asking.
Oh, did I not share it?
No, you did, but I'll bump
Maybe
this down again. Good. Okay, thanks. Yeah, or we can, you guys can run through the notebook and just keep asking questions, and we'll jump in and out as and when they happen. So I guess tell me in the chat if you would like to see us run through the notebook now.
Is this going to be fair? Is this
I don't know,
a fair poll here?
Oh, that was a very weighted question. Yes, run through it now. Okay, loads.
This looks good. I think we take the first four.
This is like the equivalent of when those cringy Twitch streamers are like, "Oh my god, it's going nuts in the chat," right? They want to see it.
Let's give them what they want. But yeah, we'll come back to the other questions at the end. I think we should have time.
Okay, cool. And I can try and answer some on the side.
Great. Okay, so I shall dive into the notebook. So hopefully you all have the notebook. Well, if you want to run through it, otherwise, I'll be running through it, so I will talk us through it as well. But yeah, it's a Colab notebook, so it should just work if you want to click through it as well. Okay, so yeah, our task here, this is a very simple task, and we will share a notebook for a much more or a more advanced task as well later. But we'll start nice and simple just to demonstrate the core concepts. So task here is we have these penguins. Some of you might have seen this data set before. It's very similar to the iris classification data set. It's nice and simple. Basically, we have 3 species of penguins, and we want to classify the species according to just 2 features, the the bill length and the bill depth. So first things first, this is all Python based. So, we just need to pip install this Palmer Penguins package, which gives us a data set. We're going to use Seaborn for visualization, and we're going to pip install Alibi Detect. As I mentioned, that's the library that we develop, one of the libraries we develop here at Seldon. It has, you can find it on GitHub, and you click on here and you can see the documentation. So definitely encourage anyone who's interested to visit our docs after the session and learn more about all the different tools that we offer. So it's just a simple pip install to install it. And if you click through on that, it should start downloading and installing the packages. Now I'm hoping my Colab notebook hasn't timed out so that I can just skip that step. We will see. Yeah, so it seems okay. Definitely, if you're running through it yourselves, please do click install, and then it shouldn't take too long. So first things first, I'm going to download the data. And we have a quick look at that. You see, every data instance is just like tabular data. Every instance has a species. That's kind of our output variable of interest, the thing we want to predict. And then there's a bunch of features here. There's actually what 5 or 6 or 7, but we're going to drop all of the features so that we're just left with the 2 I mentioned, the bill depth and bill length. So if we go ahead and plot those, we'll basically, anyone that's familiar with the iris data set, we were commenting earlier actually just how similar this data set looks. Obviously it's a different application, but we just have these nice, very well separable classes when we separate by bill length and bill depth. Nice and easy. So first thing we're going to do is we're going to take this data, nothing particularly fancy here. We're going to split it into 3 data sets, a training data set to train our classification model on, a reference data set that we're going to use in our drift detection. So that's basically from the same distribution as the training, but we pick different instances. It doesn't actually really matter in this case, but some of the types of algorithms we use for drift detection, it is important to do this so that you actually don't get overfitting of your drift detector, but it doesn't matter too much in this case. And then we'll have a test data set that we use for evaluation. And okay, so first things first. We have our data and we want to train a simple classification model. We're going to keep this really simple and just pick a nice shallow 5 deep, or even less maybe, decision tree classifier. And we're going to train that on our training data. Ed, when you can you just, or if I'm going too fast, if anyone says I'm going too fast, can you just call me?
Yeah, of course. As we mentioned earlier, right? Throw things in the chat if you want us to recap on something, put it in there as well. But for now, no comments since you started running through, so people are listening in.
Excellent. Okay, so we have a decision tree classifier, and we'll just check the accuracies on the training and test splits, and pretty unsurprisingly, it's doing pretty well on the training data and not too bad for the decision tree on the test data. So all good. Okay, so now we get to what you're actually here for, which is the drift detection. Now, of course, this data set's lovely. It's lovely and simple. You've got cute little penguins. The problem with it is that, well, for this particular example, there isn't actually any drift. If we look at our 3 splits of data that I did earlier, I've done these simple train test splits all from the same data, and the sample size is big enough. There's not going to be any real significant differences between these three splits so that there is no drift. So the first thing we have to do for the purposes of this example is actually do some stuff to our different data splits in order to induce drift for the purposes of the example. So the first thing I'll do is just I copy, make a bunch of copies of the test data, because that's the one we're going to induce drift on. And then first thing we're going to do is apply covariate drift. So remember, covariate means this is drift to our inputs, or x. And so I'm going to apply drift or shift in the data set by altering the build depth of just one of the species. So I pick the Gen 2 species, which just happens to be y equals 1. And I subtract 5, that's going to be 5 millimeters from x, just for that one feature, the first feature, which is the build depth. So that's covariate drift. And then also, for the purposes of our example, I want to induce concept drift. But you could also, as I think as Enrico was trying to point out earlier, these sometimes concept drift is similar to, in some ways, it's similar to output drift. They can be kind of multiple things at once. So I'm actually, to apply concept drift, I'm doing something to y, but we're calling it concept drift because it's like changing the process, the process of y given x. So so I'm applying concept drift by changing our two species up. So I'm essentially I'm keeping x the same, but I'm switching the labels 1 and 2 in our output data. Okay, so I've done something to these different data splits. We don't really need to look at this. This is just like a nice utility function to visualize what's going on. So yeah, don't worry too much about that. Now we'll run this nice plotting function. And here we go. It's always much easier to see what's going on with visuals, I think. So on the top left, we have a visualization of the reference data. So remember, the reference data was just was generated by splitting our training data up. So essentially, you might know this as validation data as well. It's data. It's from the training set, but it's not the same instances that the model was trained on. But yeah, so you can see the model's performing well. Good accuracy, and then we have the no drift case. So this is basically similar to the case, the reference data case, but the no drift case is on the test data. So the model is always also performing well. Slight change, but nothing to worry about. And now the two interesting ones. So this is very similar to the example we had at the beginning, this covariate drift, where you see we've subtracted 5 mil from the build depth, so the green instances have been offset by 5 mil. But actually, in this particular case, it hasn't really affected the model performance because it's still within this sort of decision boundary of our classification model. And then final example with the concept drift, we've essentially flipped the colors. So we've flipped the labels between the green and purple. So unsurprisingly, the model accuracy has been hit a lot here. It's very bad. So these are the two, well, these three here, the bottom two and the top right-hand one, are the ones that we're going to basically give to our drift detector and see what happens, essentially. So you can imagine these are different data sets we might see during deployment. And we want to identify if these different data sets have drifted from the top left one, our reference data, which is the distribution of data we train the model on. Okay, so we're set up, and now to actually use Alibi Detect to monitor for drift. So before I actually get into talking through what's going on here, I should probably just start by saying all the drift detectors in Alibi Detect, we imported this right at the top. So they can be imported by just doing this here. So from Alibi Detect.CD is the submodule where the drift detectors are, import, and then the name of the drift detector. So we're going to import and talk through a few different ones here. Okay, so the first thing we're going to do is we're going to try out what we call unsupervised drift detection. What we mean by unsupervised in this sense is that we're not using labels. So we are doing drift detection purely on X, our input data. So to set up a drift detector, we basically just give the drift detector one mandatory argument, which is xref, the reference data. So this is going to be the data that that we called P of Z earlier. Sorry, P of Z ref earlier. It's the data that we're going to compare to when we do our drift detection. So it's xref is usually your reference data will be drawn from the same distribution that you trained your machine learning model on. So the exam question is, has your deployment data drifted away from this reference data? And the next argument, that this is optional, but we normally set it. We set a keyword argument called p-val. This is essentially, this is what I called alpha earlier. So this is the threshold. If your p-values in detect, if the p-values that your detector predicts when it's doing its tests for drift, if they're below this threshold, we're going to flag drift. So this is this is that alpha value. Okay, so we instantiate our drift detector. And now what I'm going to do here is I'm just looping through the different data sets that we generated earlier. So XS just contains those three different data sets. Contains the X test, which is the X data where there's no drift. Contains X covar, where we applied that offset to simulate covariate drift. And it contains X concept, which is where we simulated concept drift. Okay, so yeah, we're going to iterate through, and we're setting random seed each time, just for reproducibility in the notebook. Of course, you wouldn't do that in production. And then we're going to call, the important bit is we're going to call the .predict method of the drift detector. And here we give it, just X. So here we give it the deployment data. So this here is the data that we want to compare to xref. We want to see if this has drifted from xref. So when we call .predict, we'll get a dictionary, a results dictionary out. And the important bit is that in the data, within that dictionary, there's various things it can tell you about the prediction result. It can tell you if the data, if drift is occurring, it can give you the p-value, and so on. Okay, so there we go. So we're getting three different values here because we applied our drift detector to these three different data sets. The no drift one, where we've simulated covariate drift, and a concept drift one. And this is the result we get. For this is kind of reassuring that when we know there is no drift, the drift detector says it hasn't detected drift. And the reason it's done that is because if we look at the p-values that it's returned, and just I guess something of interest here is you see that there's two p-values. That's because the KS drift detector is a univariate drift detector. So it returns a p-value for each feature, each dimension in your data. And that's why there's two p-values, because we have 2 dimensions here. So yeah, it's telling us that there is no drift in either of our feature dimensions. And I'll just take this one question. I think that's a good one from admin. Wouldn't it make more sense to just plot the drift? And I guess what he means is like, yeah, well, in this particular case, a human can eyeball this and say, you can look at it and say, oh, there's drift, or oh, there's not. But quite often, if you're applying, like, if you're deploying a model on text data, we'd probably be applying this to like our embedding or latent space with like 700 or 800 dimensions. So it's not easy to plot if it's not very low dimensional. And of course, you might not want to have a human in the loop. You might want to have a drift detection deployment that's just always there, always monitoring, even when a human's not looking at your visuals. So in the no drift case, no drift detected, p-values are above the threshold. Now in a covariate drift case, where we have this obvious shift in our covariates, we do detect drift, which is good. And we detect drift not because, so it's confusing because it's done it in scientific notation here, but you see the p-value for the 0th dimension is the same as before, because we haven't got any drift in the bill length or the x direct, so the first dimension. We have got drift in the second dimension, and that's where we see the drift detector is telling us that. It's telling us that the p-value is very close to 0, so it's very confident, because the p-value is small, that there is drift in the second dimension. So we're detecting that, and we could action on it. Now, this is an interesting one, an important point here. In the third case, where there's concept drift, our drift detector is not detecting that. You see the p-values are both large, and we're not detecting that there's drift. Now, the reason for that is that there is concept drift. We flipped our labels, but there is no drift in the covariates. So when we have set up a drift detector, which is just monitoring the covariates x, that is not going to detect all types of drift. If you've got drift that actually, if your covariates are not drifting, but there is something going on in your system. So yeah, and that's the first kind of, I guess, the learning outcome of this particular bit of this example is that one type of drift detector monitoring one thing is not always enough to monitor your entire ML system. So what can we do about that? Well, that was unsupervised drift detection. We can do supervised drift detection. So whereas unsupervised, we're monitoring X. When we talk about supervised drift detection, what we mean is we're monitoring, we're doing drift detection using labels or ground truths. So typically what this involves is monitoring model loss streams. So all we're doing here is we define, for those same data sets, we define, like data splits, we define simple binary loss streams. So all we're doing is we're comparing when the model predictions equal the labels. If they're equal, we assign a 1 to that instance. If they're not equal, we assign a 0. And just an example, this is what that looks like. So 1 means a correct classification, 0 means an incorrect. And so for this type of drift monitoring, when we're monitoring Bernoulli streams or like binary streams of just 1s and 0s or falses and positives, we wouldn't use the KS drift detector. For that, we have a different drift detector called FET, or Fisher's exact test. So what we do to set this one up is we give it the reference loss stream. So that's a loss stream on the reference data set. Again, we can give it a p-value. So this is like the p-value threshold. And here there's another interesting one that we can define, which is this is a one-sided test, a statistical test, which means we have the option of defining our alternative hypothesis. So by defining it as less, that means we're only going to flag drift when the model's performance has degraded, when the amount of zeros has increased relative to 1s. So of course, if you cared about a change in either direction, you could say two-sided. If you only cared about this metric increasing, you could say greater. So we set this one up, and we do the same thing. We iterate through our 3 data sets, and we'll get something kind of similar. So in this case, reassuringly, we're not detecting drift on the reference data set. Interestingly, we're also not detecting drift on the where there's covariate drift occurring. And again, that's because remember now we're actually monitoring the model accuracy, and the model accuracy has not decreased here. The drift is, even though the covariates are drifting, it's not malicious to the model. So doing supervised drift detection, monitoring model accuracy will not detect this type of drift. But as we desire, if we do this supervised drift detection, we do detect concept drift, and that's because the model accuracy has significantly degraded. So, two learning outcomes there. We've looked at the different types of drift, learning outcomes, I guess. We've looked at how to actually use Alibi Detect, and I guess we've seen that important point in action that it is, or at least what we do is we will use numerous different types of detectors at once on different data streams to make sure we're kind of covering all the different angles. But of course that's very simple. What else could we have done on this particular example? The thing that we didn't demonstrate, but we have the tools to do, is we could have monitored drift, or maybe not using decision tree, but like if this was a random forest, you can get like a measure of uncertainty in a random forest, jackknifing, or if it's a neural network with like a notional uncertainty, we could have used, we have something called the classifier or regressor uncertainty drift detectors. So welcome you to click through the links and you can read the docs. So this is set up to monitor drift on a model's uncertainty. A pretty cool thing you can do actually is we have a drift detector which actually uses your own classifier model to detect drift. So if you have a super powerful classifier you train that works really well on a certain data set or type of data set, you can actually harness that to detect drift. This is a nice simple data set because it's tabular, but it's all numerical data. If it was mixed and you had some categorical variables, then we use a slightly different drift detector which can handle mixed type, so categorical and numerical data. And then something we'll kind of touch upon towards the end, well, quite soon, what I want to talk about here is we have a drift detector that can take context into account. So yeah, that's an introduction. I was going to go back to slides and talk about some sort of more advanced topics, but is there anything?
Yeah, a couple of things I thought we could talk about live, which would be interesting. So Graham asked, do you think it's possible or useful to monitor drift in a recommender system, or will any interaction between the user and the recommendation environment constitute conceptual drift? And I had to think about this a little bit, right, and the way that it works. But actually, yes, it is still possible, and actually probably very important, right? Because sure, your individual point has changed, but the way that your user has, let's say, interacted and bought some different things, right, the next day, that individual user is not what we're trying to detect drift in. What we're trying to detect drift in is like this statistically across the board, like do all of our users look different? And that's something we're trying to understand is, did everyone add loads of things to a cart during a day? Maybe that is important. We do want to detect it. Whether Ashley added something to a cart when he doesn't normally is not. It's like that's an individual point. And what we're doing with drift detection is looking at a distribution, right, that we want to monitor. So yes, you can apply it. And there are probably, depending on which types of drift you're looking for, some will be more important than others. I guess with recommender systems, it's quite hard to know exactly how well they're working because yes, you get feedback in terms of whether someone bought a product or not, but what you don't get is Ashley looked at that, we recommended it, he looked at it, he actually went and bought it somewhere else because it was cheaper or something. So the recommender system did do a good job, but we didn't capture it, or we capture it as a failed prediction or something. That's why they can get quite tricky. I don't know if Ashley, if you want to add anything on that, or does that kind of cover Graham's question?
I think so.
Cool.
I can answer the bottom two.
Yeah, do you want to answer that one then? I answered Sean's already in the chat.
Oh, nice.
Okay. But if you want to save us one, that would be good.
Yeah, so the question on can FET drift be used for regression problems? Yeah, really good question. Answer is no. Or generally, it depends on your loss stream, but for a regression problem, your loss will probably be like a floating value, like I don't know, an accuracy score or a square root RMSE error or something. So you would usually not use FET. For that, we have one called CVM, Kramer von Mises, which is designed to be used for regression problems.
There was also another question Murad had asked earlier. So he asked about understanding the difference between univariate and multivariate tests. And he says whether the two types cover all types of drift, or are there certain types of drift we don't know how to find out?
Whether to use univariate or multivariate tests, it's not so much about the different types of drift. With the exclusion of doing supervised drift detection, where if you've got a very low dimensional loss stream, then you would usually use the FET or CVM, or we do. Whether to use univariate or multivariate is more to do with your type of data. So for what we're about to get onto and talk about, when you're sort of doing stuff on text or image data, we tend to use like multivariate tests. For tabular data where you care about feature level drift detection, so getting separate p-value for each feature, then we use univariate tests. Yeah, so I think that's probably a good point. That's a good a good point to move on. I think.
Yeah, I just stuck a link in the chat there. That maybe you could show it live quickly. Actually,
sure.
If you jump in and I'm just on the algorithm overview page. Because there was a couple of questions around like what was the name of that algorithm? Obviously, we just announce it quickly and expect you to remember Kolmogorov Smirnov or something, right? I never pronounced that correctly. But yeah, this algorithm overview page is really useful, right? Because it shows all the different types of drift detector we have in there, the like modality of data that it applies to, whether there were a bunch of questions around how do I do drift detection once my model is actually deployed, and that's the column you can see on the right hand side around online drift detectors, which is basically comparing like statistical windows of inference data against some sort of reference set. So have a look at that, right? It's a really good place to start, and then you can dig in and understand a bit more about each algorithm.
And just as a kind of there's also all our examples kind of go into more detail there. There's loads of examples on different data modalities, and then there's also like a background page, sort of to talk about lots of. Now it's like I've just stolen all the images. I haven't.
Well, you did write the background page. You're allowed to steal your own images.
Yeah, there's a background page on sort of talking through lots of this in more detail, a little bit more maths, but not too much maths. Right, but yeah, so I see we're not running out of time, but we're coming towards the end. So I quickly want to finish on just quickly going through one more topic. If I can restart the slides. Okay, so yeah, so that's great. We talked about drift, different types of drift, some of the different drift detectors that you can use. But I guess people have probably noticed, that's a very simple data set, probably quite different to what lots of you guys and girls like to see in real life. Yeah, basically I want to talk about how we can actually extend all this to more advanced real world sort of data sets and modalities. So just coming back to, we showed this before, you have your reference data set, you have your test data, you compute some sort of test statistic or multiple test statistics. From that, you compute a p-value, so you do this hypothesis test, and you compare it to a threshold, and then you make the detector makes a decision, yes, there's drift, or no, there isn't. But how do we tackle more complicated data modalities where your data is not just nice numerical vectors of continuous data? An example being images. How do we, here we have reference data. We have a reference data set of images, and then in deployment we actually see that our images are more pixelated. How can we detect this sort of thing? The answer is we do some sort of pre-processing. So we do some pre-processing to pre-process our images such that they also look like just nice numerical vectors before we pass it to the drift detector. And the nice thing is that pre-processing, you don't usually have to design something from scratch. Chances are, if you want to detect drift on images, you're probably already working with some sort of ML system that takes in image data. So, in this example, we might be doing classification of these images, in which case you'll already have, as part of your classifier, you'll probably have an encoder to take images and encode it into some sort of latent representation. Message here is that you can recycle your existing ML model components to pre-process various data modalities into a form that you can perform drift detection on. Just an applied example, we'll share this link in the, didn't mean to do that. We will share this link in the chat for you to go through in your own time. So as this notebook, basically it's an example on text data this time. So you've got these newsgroup posts. And the task here is you're classifying these newsgroup posts by topic. So the one I'm showing here as an example is on like a post about baseball, I think. So here you have some classification model. At the moment it's a black box. We don't know what's inside it. And well, if it is a black box, so you can't actually recycle it as such. It still probably gives some sort of softmax outputs and then a predicted class. So for sure, if nothing else, you can perform drift on these two things, on the model outputs. And so there you'll be monitoring for output or prior drift and also concept drift if you have labels. But where it gets really interesting is if you can sort of peer inside the model. Like here, we're opening up the model and we see that it's some sort of it's an Esper sentence transformer, which transforms or encodes a newsgroup post into like a 384 dimensional embedding, and then those go into a classification layer. In this case, we can now perform drift detection directly on the embeddings. So this is not that dissimilar to the penguin example we looked at. Instead of 2 dimensions, we have 384. And yeah, you could apply drift detection on this. Now, how many more questions do we have? Shall I go into context drift?
Yeah, you can go into it. We don't have any more questions though.
Oh, nice. Okay.
I haven't typed 2.
So that's the main message here is that if you can open up your model, you can recycle it to also perform drift detection on your inputs as well as the model outputs. If that model has a notion of uncertainty, you can perform drift detection on that as well. Now, this is just this thing I'm showing down here is just a simple. It's not that simple, but it's a 2D visualization of these 384 dimensional embeddings, a UMAP visualization. I'm going to use this just to demonstrate what happens in this example. An important point is that you could perform drift detection on this 2-dimensional space, but you don't need to be able to find a low-dimensional representation in order to perform drift detection. This is just to aid out the visualization of this example. Okay, so what happens in that notebook, which I won't open up, but do, if you're interested, go through it in your own time. We have some reference data. So this is showing like a 2D visualization of the embeddings of our reference data. So just 2 topics here. We have, I picked 2 topics I find interesting. So one is to do with space, one is to do with cryptology. And the way that we would do what I just described here, the way we would use Alibi Detect on this example when we want to recycle this pre-processing component, is we simply define a pre-process function, which is a wrapper around that embedding model. So we have our classification model, which is this entire thing, but we just want to use the sentence transformer, the embedding model, so that we can get embeddings out. So we define this pre-process wrapper, which all it does is it takes X, which is a list of news group posts. It passes them through the embedding model, the sentence transformer, within our big classifier model, and then it returns that transformed X, which is now 384-dimensional vectors. And then all we do is we do the same that we just did, but in this case, we're using MMD drift, a multivariate detector, for the reasons I mentioned earlier. This is it's likely that some of these embeddings will correlate to each other, and it makes much more sense to use multivariate detector in this case. We're setting it's a PyTorch backend, so it's going to run really nice and fast on GPU. And then the kind of added interesting bit here is that we set a pre-process function. So this will be applied on all the data we give this detector, so the reference data and the deployment data. And then what happens if we do that? Well, now we call predict on this particular bunch of data. This is data where we know there is no drift, just as a test. So the instances are different, but it's not the same instances, but they're drawn from the same distribution in which we know there's no drift. And yeah, we get the detector telling us there's no drift. The p-value is close to 1, and the test statistic, the MMD squared, is small. And now in this case, it's pretty obvious drift here, because we've introduced an entirely new topic. But of course, in your case, the drift might not be that obvious. And we're again calling predict. And now we should see that there is drift, and the p-value is very small. This is like quite obvious drift. And that's it. So kind of the same sort of process that you saw in the penguin example. And a final cool thing, which we're quite excited about, we've just published a paper on this, is how can we account for context, known context that we wish our drift detector to take into account. And to just demonstrate what I mean here with a simple example, let's say we have 3 topics here. We have cryptology, space, and politics. Now, what happens if around election time, we're going to have more politics topics appearing in our deployment data? This is drift, but it's not harmful. It's more topics, but our model is experienced with this sort of topics. It's not going to affect our model performance. However, a normal detector applied to this covariate data, this input data, will flag drift here, because even though it's not harmful, the distribution of our input data has changed. So basically, how can we give our drift detector context, for example, the time of year, to say, hey, it's election time right now, so don't worry about the drift. We expect to see more politics topics around election time. And we can use that with the context MMD drift example. Here we give it reference data, but we also give it context data that we wish it to take into account. Of course, that's quite a quick explanation of this, but in the notebook that I linked, we have a much more in-depth applied example of this, because it's quite an exciting but somewhat difficult thing to get your head around.
I think it's also something that actually, when you think about it, pretty much all drift that you'd want to identify has to account for some sort of context, right? Even if you use the recommender example that I can't remember the name of somebody else earlier, identifying that statistically all of your users are buying more electronics, right? Within the context of it being Black Friday is totally normal, if you can.
Sure. But
even in an applied scenario like that will get flagged as drift. Now maybe that's okay. You can just go, that's Black Friday. We'll ignore that, right? But if you're using context-aware drift detector, it would be, well, given the time of year, as you said, with an election, it's actually totally normal to have way more electronic sales. And yeah, that's pretty much how, it's how real world things work, right? We do have context in everything we do.
Yeah, so just to summarize, and someone's asked us to share the paper slides, which actually I think is a final point on this.
Oh, well, there
We'll
you
get to
go.
that. Yeah, so summary, big obvious point here, but I would recommend, or we recommend, that you detect drift before it's a problem. Think of that Zillow example. It's much easier to be monitoring for this stuff and manage and act on your detections proactively rather than be reacting after the fact. Monitor different types of drifts. That penguin example we talked through. If you monitor different types of drift, you have a much better chance of actually detecting when something is happening. Oh, nice one. And an important one here, if you've got nice, simple data, you might be able to apply a drift detector straight away. But also, it's not a problem if your data is more complicated. If it's image data, text data, even graph data, you can still quite simply monitor drift on it, as long as you recycle existing machine learning components and use those as in pre-processing. And so either the library that we mentioned, and maybe we should just share like a link to it at the end.
Yeah.
But that can do all of this, plus we've not had enough time to talk through lots of what it can do. But please do check out the documentation if you're interested. It can do interpretable drift detection, so looking at actually when you detect drift, what is causing that drift. It has online drift detection that Ed sort of mentioned. So that's instead of applying drift in an offline sense, where you're applying it to batches of data at a time, you can apply it to single instances as they come in using like moving windows. And context-aware drift detectors, which we just talked about. And I think that's it. Do you want to just share the online drift detector?
Yeah, I was going to do it. I stuck it in a reply to your
nice.
So what I'll do is I'll put it out for everyone to see. And then the other thing I will do is I will just, someone asked at the beginning for the slides. Let me just go and get that link again. Because I'm sure this is always the bit where people go, oh, thank you so much. Can I get a copy of the slides? And the answer is yes, of course. Just give me a second to find the link.
If you can find it in 2 minutes.
We're good. Okay, good. Got it. Okay, and those are the slides.
Yeah, thanks so much. And I guess I don't know if we did miss any questions. People would definitely should feel free to.
Yeah, actually, the final thing I'm going to do, and this time I've only got like 30 seconds to do it. I'm going to send a final link into the chat here, which is to join us on Slack. So we have a Slack community where you can come in, you can ask questions about Alibi Detect or any other kind of open source stuff that we do. It's a really good place because you can actually interact with us, right? And if you have issues or you just need help getting started, jump in there. And yeah, we're all on there. You can ask questions, and also you'll get to find other people who are using Alibi and share your experience with them. It's a good way to get in touch. Otherwise, you've got a lot of contact details on the screen in front of you. You've got the slides, you've got the links to everything. Thank you all so much for giving up your time and listening to this, and hopefully working through we didn't get any questions about the actual workshops. I'm assuming everyone ran their notebook perfectly well. So well done for being such a great audience. Thank you.